Right, so what we want to look at now is we want to look at joint probability distributions, right? Okay, so your joint probability distributions first would be split into two cases, discrete and continuous, right? For discrete, you're going to have a joint probability distribution. In the discrete case, you're going to have joint probability mass function, right? And in the case of for continuous random variables, what you're going to have is you're going to have a joint probability density function, right? Okay, so first one we'll talk about is joint PMF, right? Joint probability mass function, right? All right, so for the joint PMF, what I'll do is I'll do this example over here, right? Because the theory, at least the definition over here, may be a little bit on the complicated side, so I'm gonna do this example, right? And this over here, what we'll be doing is we're going to be getting a joint PMF, right? A joint probability mass function, right? Okay, so I have this standard experiment over here where I have a fair coin and I'm tossing it 3 times. So I tossed coin 3 times. For these over here, these fairly simple examples, we could in fact write out what the sample space is, right? Notice over here, you could regard this as a 3-stage experiment where each stage you have 2 possibilities, right? So overall, what you're going to have is the amount of possible outcomes would be 2 times 2 times 2, which is 8, right? And as listed over here, right? And I think I already did this example, at least showing you what the sample space is. So these are possible outcomes when you toss your fair coin 3 times in succession, right? You can get, say, 3 heads or 2 heads and a tail and so on, right? This being a fair coin means that the probability of each outcome over here is 1/8, right? Because you have 8 possible outcomes and the outcomes are equally likely, right? Alright, so with this experiment and with this sample space, right, what we have is we have 2 random variables, right? First random variable is x over here, right? Big X, right? And x is the number of heads that you get on a first toss, right? Right, and then also y, you have a second random variable, right? Which is the total number of heads that you would get on an outcome, right? Okay, so first of all, if you have an experiment and you have, say, 2 random variables associated with the experiment, and you want to see how they interact, if you want, right? Or what's the probability of both of these occurring at the same time, right? Then what you need to do is you need to use a probability mass function, right? Okay, so what I mean by occurring at the same time is this over here, right? This problem is asking you probability that the random variable x, big X, is equal to 1 and random variable big Y is equal to 2, right? Now, how you want to read this comma over here is you want to read it as probability the big X is equal to 1 and the probability Y is equal to 2, right? So both of these over here are occurring simultaneously, right? Okay, so what I have in this diagram, hopefully it's not too confusing, right? First of all, I have my sample space over here, right? So this is the set of possible outcomes here, right? You have 8 possible outcomes, right? Okay, and then what you have is a random variable x over here, right? Now what the random variable is doing for you is for each outcome in your sample space, your random variable x is associating a number to that outcome, right? So for example here, the big X over here is the number of heads on the first toss, right? So if you're looking at these 3 heads over here, right, the first toss is a head over here, right? Okay, so the number of heads on your first toss over here is actually equal to 1, right? And likewise for this outcome over here, right, if you consider this first outcome, if you consider this outcome over here, right, and you consider the first toss, right, what happens on the first toss, right? The first toss, in this case, you have a head, right, and the value of the random variable for this outcome over here is equal to 1, right? So remember what your random variable is doing for you, right? Your random variable is assigning a value to each of the outcomes in your sample space, right? At least that's the definition that you want to use in the discrete case, right? Okay, so this particular one over here, let's say consider the tail head head, right? The tail head head, well, what is the value of x associated to that, right? The value of x associated to that is what you do is you're supposed to be looking at the first toss, right? Look at the first toss, and the number of heads that you have over here in the first toss is actually 0, right? Because you have a tail, right? So this over here, the value of this, for this outcome, the value of the random variable for this outcome is in fact going to be equal to 0, right? Okay, now what I did in this diagram over here, because I'm going to use it a little later on, right, is I'm showing over here all of the 4 outcomes in the sample space that have value 1 for a random variable x over here, right? And you see over here that you can actually think of your random variable x as a function, right? As a matter of fact, it's in fact defined as a function, right? But I'm not going to get into the huge amount of details as the random variable being defined as a function. What you want to do is you just want to realize that for your sample space, the random variable is associating a value to each outcome in your sample space, right? So this guy over here, this outcome over here, the value associated to it is because how the random variable is defined is the number of heads on the first toss. If you look at this outcome with the 3 heads, on the first toss you have a head, right? So the number of heads on the first toss is 1, right? So that's why you get the value 1, right? Alright, okay, and you have a second random variable over here, which is y, right? So for the same experiment in the same sample space, right? Y is the total amount of heads, right? So for example over here, right, for this outcome, right, if you look at this outcome, the number of heads that you have over here is 2, right? So for the random variable y, right, what you're doing is you're computing the amount of heads over here, and the amount of heads is 2, right? So for this outcome, the value of your random variable is 2, right? And likewise, this one over here, the head, tail, head, right? For this outcome over here, the value of the random variable is also 2, right? For this one over here, right, where you have 3 tails, right, the value of the random variable y is in fact 0, right? Because, well, the number of heads in this outcome is actually equal to 0, right? Okay, so now what we want is we want to determine this over here. We want to calculate this, right? So this is probability that random variable x is equal to 1, right? And probability that random variable y is equal to 2, right? Okay, so what you're doing over here is you in fact calculating a value of a probability mass function, right? Okay, so what a probability mass function is that it's a function, right? So what that means is that if you want to be able to calculate this for any possible value of x over here and any possible value of y, right? And later on, well, I actually do that, right? Here I work it out. So for example, when the x is equal to 0 and y is equal to 0, I'm going to get a certain value. When x is equal to, say, 0, y is equal to 2, I'm going to get a certain value, which is 1/8. Okay, so for the possible values for the big X and the possible values for the big Y, what I want to do is I want to get a probability, right? And as you probably saw in Ms. Bhutan's class, you can organize that in a table, right? So we will get to the table in a second, right? Okay, so now what's your range of values here for the X and the Y, right? Well, the range of values for the X is 0 and 1 because this is the number of heads you can get on the first toss, and the range of values of y is the total number of heads on an outcome, and the total number of heads can range from 0 to 3, right? Okay, so for this probability mass function, right, the possible values over here for the constants would be either 0 or 1, right? And over here for the y would be 0, 1, 2, and 3, right? Okay, and specifying specifying each of those values, right? Okay, and let's get to the table, right? Specifying each of those values. So for example, in this table over here, you see in that this over here, this is indexing the x values and this is indexing the y values, right? Okay, so for example over here, this entry, this 1,8, this is when the small x is equal to 0 and the small y is equal to 0, right? And when the small x is equal to 0 and the small y is equal to 0, you have a probability 1,8, right? So this is describing your probability mass function, right? What the probability mass function is doing for you. It's calculating probabilities that when you have two random variables and each random variable is taking some specific value, right? And the specific value is coming in pairs, right? A value for the small x, such as the 0, and a value for the small y, such as the 0 over here. Alright, so let's work out this problem over here. Probability x is equal to 1, y is equal to 2, right? So what you're doing is you're working out, you're evaluating your probability mass function at a specific case when the x is equal to 1 and when the y is equal to 2, right? Okay, so do we do this, right? Well, what we look at, so let's just recall what our sample space is, right? Sample space would be your 8 possible outcomes, right? And because it's a fair coin, each of these outcomes is equally likely, so the probability associated to each outcome is 1/8, right? And now what I want is probability x is equal to 1 and y is equal to 2, right? Now, what are the cases when x is equal to 1, right? Well, x is equal to 1 means that you have a head on the first toss, right? So these are the four cases where x is equal to 1, right? Head, 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 tail, tail, head, head, tail, and then head, tail, head, right? And notice all of these, if you the value of the random variable x for each of these four outcomes is equal to 1, right? So that's what these arrows over here mean, right? The values of your random variable would map to this 1 over here, right? Okay, and then y is equal to 2 would be, remember what y is equal to 2 is supposed to be. Y is the total number of heads, right? Okay, so y is equal to 2 would be the cases when you have exactly two heads, right? And it's these three cases over here, head, head, tail, head, and tail, head, is when you have exactly two heads, right? Okay, but what I want is probability x is equal to 1 and probability y is equal to 2, right? So notice over here, I have this is when probability x is equal to 1. If you want a little nicer notation, right? The cases when x is equal to 1 is what you're doing is you have this 1 over here. This x here, this random variable, is a function from your sample space. So x inverse 1, what you're doing is you're taking the pre-image of the 1 over here, right? So when you take the pre-image of the 1, it means you're looking at all the elements in the sample space that actually map to this one, and it's these 4 over here, right? So all of them that map to 1 is x inverse 1, and it's what I just said. It's these 4 outcomes over here, right? These 4 here, right? Okay, and then y inverse 2 would be all that map to 2, right? Under the random variable y, right? In other words, all outcomes over here where you have exactly 2 heads, right? Okay. Right, so this is your y inverse 2. Y inverse 2 consists of these 3 cases over here, right? What I want by x is equal to 1 and y is equal to 2 is that it must satisfy both conditions, right? Now, this x inverse 1, right? All the cases when x is equal to 1 is actually an event of your sample space. And that event consists of these 4 cases, right? Y is equal to 2 consists of this event over here with these 3 outcomes over here. And in order to satisfy both x is equal to 1 and y is equal to 2, you take the intersection of the 2 events, right? And the intersection of the 2 events, so this is when the x is equal to 1, this is when the y is equal to 2, right? And what you want is outcomes that satisfy both of those. So you need to take the intersection of the event that corresponds to x is equal to 1, event that corresponds to y is equal to 2. And here, this is the intersection of the events would satisfy both x is equal to 1 and y is equal to 2, right? So notice both of these over here, right? You have 2 heads, right? So that satisfies y is equal to 2. And both of these over here satisfies x is equal to 1. You have a head in the first position for both of these, right? All right, so to get probability x is equal to 1 and probability y is equal to 2 is the probability of this event occurring, right? And the probability of this event occurring, well, this is just a subset of your sample space, and we know how to calculate probabilities of a event, right? In this discrete case, right? What you do is you just add up the probabilities for each of the outcomes. You're going to get 1/8 here, 1/8 for this one. You get 1/8 plus 1/8, which is a quarter. Right? So the second part of this question is what we want is the joint PMF for the random variables x and y, right? Okay, so remember what your joint PMF is, right? The joint PMF is you want to work out probabilities such as these for all the possible cases of the x and the y over here, right? So your possible cases of the x would be 0 and 1, and the possible values for the y would be 0, 1, 2, and 3, right? So you have 8 cases altogether, right? And you want probabilities for each of those, right? We already worked out one case over here. We got the answer, which was a quarter, right? Now, how you can state your PMF is you can state it in a table form over here, right? So notice in this table over here, you're going to have 8 entries. This is indexed over here by the x values, and this is indexed over here by the y values, right? So your possible values for the x, as I said, would be 0 and 1, right? Possible values for the y would be 0, 1, 2, and 3, right? Okay, and to get your joint PMF means that you want the probability from each possible pair of values for the x and the y, right? Okay, so for example, you'd want, well, these are, I worked out one already. This is x is equal to 1, y is equal to 2. And I need 7 more, right? And the 7 more I actually worked out here in the notes, right? It's 1, 2, 3, 4, 5, 6, 7, right? So the 7 other cases, it's over here, right? Right, I won't do all 7 cases, but let me do a couple of these, right? So let's say I want probability x is equal to 0 and y is equal to 0, right? Well, x is equal to 0 means what, right? X is equal to 0 means that, remember what x is saying that you have a head on, is the number of heads on your first toss, right? So if x is equal to 0, it means that you have no heads on the first toss, which means that you have a tail on the first toss. So having a tail on the first toss would in fact be these 4 cases, right? So this is when x is equal to 0 over here, right? Alright, and then y is equal to 0. So y, well, what is y? Y is total number of heads, right? Okay, so for you to have y is equal to 0 means that the total number of heads is 0, right? And the only way the total number of heads is going to be equal to 0 is really just this case over here of all three coin flips being tails, right? So this over here, this is y is equal to 0. X is equal to 0 would be these 4 bottom ones over here, right? And for it to be x is equal to 0 and y is equal to 0, right? It means you need to satisfy both x is equal to 0, which is these 4 cases, and y is equal to 0. In other words, you're going to be taking the intersection of these events, and when you take the intersection of these events, the only thing that's going to be contained in that intersection is when you have 3 tails over here, right? So the only case that satisfies x is equal to 0 and y is equal to 0 is this 3 tails over here. So probability x is equal to 0 and y is equal to 0 is the probability of having the outcome with 3 tails. Now this is a single outcome, right, in your sample space with 8 outcomes, so probability of that would be 1 on 8. Alright, so let's do one more case of this, right? So probability x is equal to 1 and y is equal to 0, right? So what are the cases that satisfy x is equal to 1? Well, we saw that already, right? Cases from your sample space where x is equal to 1 is you have a head on your first coin flip, which is these first 4 cases over here, right? So this is when your x is equal to 1, right? These 4 over here, right? And second one that we would need over here is y is equal to 0, right? Okay, so what is y is equal to 0? Y is the total number of heads, right? And in your sample space over here, the outcome that corresponds to y is equal to 0 is having all three tails over here, right? So this is y is equal to 0. Right. Okay, so x is equal to 1 is these four cases over here. The event consistent of these four cases. Y is equal to 0 is consistent of this single case over here. Now, what you want to notice is that the intersection of these events is empty, right? They have nothing in common, right? So what that is saying is, I mean, if you want to look at it practically, right? This over here is saying that you need a head on the first outcome, right? And this y is equal to 0 is saying that you have no heads whatsoever, right? So there's no way that you're going to have any outcomes that satisfy both of those conditions simultaneously, right? Because this means at least one head over here, and this means no heads whatsoever, right? So outcome that satisfies both x is equal to 1 and y is equal to 0, there isn't any, right? So the event, right, of both of these conditions holding, right, is in fact the empty set, right? And what we're doing is we're calculating probability of the empty set, right? And we saw that probability of the empty set is actually just equal to 0, right? Alright, so the first one that we worked out was when probability x is equal to 1 and y is equal to 2, and we got a value of a quarter for that, right? We got a probability of a quarter, right? Now, in your table here, right, and your table, as I said, is going to have 8 entries, 8 possible positions here, right? 8 positions, right? Indexed by possible values for the x here and possible values for the y, right? So this here, this row over here is for x is equal to 1, and this column over here is for x is equal to 2. And what you do is you put your probability x is equal to 1, y is equal to 2 into that position. You're going to get a quarter, right? Okay, and then you can keep, as I said, you just need to work out each of these, right? It is a certain amount of work, right? So probability x is okay, so you work out each of these and then you just populate your table, right? So probability x is equal to 0, y is equal to 0 turns out to be 1/8. What you do is you put it in position over here for x is equal to 0, y is equal to 0, right? This one that we just worked out, that probability x is equal to 1, y is equal to 0, right? This is where this row over here is where x is equal to 1. This column over here is y is equal to 0. And notice in this entry over here you have 0, right? Okay, so for the 8 different cases here, right, you calculate the probabilities and you assemble it and you put it in this table over here, right? And this is a representation of your probability mass function, or practically it is your probability mass function here, right? Alright, so what we just did is for an experiment with two random variables x and y, right? We worked out each of these joint probabilities and we assembled it into a table over here to get your probability mass function, right? So this probability mass function in fact came from an experiment, right? But it is possible that someone can just give you a probability mass function, right? And just ask you to work with it, right? So for example over here, this problem here from a past paper, right? What they do is they give you your probability mass function here, right? Notice they didn't specify any experiment or sample space or so. They give you a probability mass function, and nothing is wrong with that, right? It's the same information after you do experiment and so on. In this particular case that I just did, right? You get your, for each possible value of your random variable, you get a probability, and over here, if you want, they just bypassing all the description of experiment, sample space, and so, and they're just giving you the results, right? So they're just giving you that you have random variables, right? X over here takes value, possible values for the x would be 0 and 1. Possible values for the y would be 0 and 1, right? And they're giving you the associated probabilities for those, right? Okay, so what I'm saying over here is that your joint PMF, right, could simply be just specified by a table, right? And probably for most questions, but not all, right, for the joint PMF, you would be working with a table that's specified for you, right, without mention of an experiment or sample space for that experiment. Right, okay, so over here, this is a formal definition of what a joint probability mass function is, right? So I have two random variables, big X and big Y over here, right? A joint probability mass function is really just what I was doing above, right? Okay, so for your big X and your big Y, you have possible values small x and small y, right? And what you want a joint probability mass function is a way of determining probabilities for any value of the random variable, any value small x of the random variable big X, and any value small y of the random variable big Y, right? For any possible x and y over here, right? And as I said, usually it's given to you in a table, right? So notice over here for this PMF, right? If you forget about the fact that it came from an experiment, right? This PMF over here, the possible values for the X would be 0, 1. Possible values for the Y would be 0, 1, 2, and 3. And this f of xy over here, right, is just the information in the table here, right? So the f of xy is literally the same thing as this table here, right? In the discrete case, right? It is probably possible that you can have a joint PMF where you have countably infinite values for y or x, right? But yeah, that sort of joint PMF we're not going to look at in this class, right? So for the joint PMF that we're going to look at in this class, the range of values for both the x and y would be finite, right? In which case this f of xy is really just specified by a table, right? Okay, right, so a joint PMF is a function, right, usually specified by a table, right, that would give you the probability for each possible pair xy over here, right? Now, in order for it to be a PMF, right, well, each one is a probability, right? So for example, over here, probability x is equal to 0 and y is equal to 0 is 1, 8, right? The fact that it's a probability means that it needs to lie between, well, it needs to be bigger than 0, right? That's what this is saying over here, right? And then if you look at the sum of your probabilities, now remember, this is just to go back to the fact that this came from a sample space of an experiment, right? Each of these disjoint correspond probabilities for disjoint events, right? And if you add all the probabilities here, right, the events for each of these probabilities would cover all of your sample space, right? So if you add up all of these probabilities must add to 1, right? So that's where this second condition comes from, right? So in order for this example PMF over here, right, to be legitimate, right, each of your entries over here needs to be bigger than or equal to 0, and the sum of the probabilities in the table has to be equal to 1. Alright, so let's talk about marginal distributions now, right? So the idea is that you're given a PMF over here, right? So you're given probabilities of this form, right? You're given these joint probabilities here, right? What we want to do is we want to recover if you want normal probabilities, right? So given a joint PMF here, right? What we want is a normal probability, such as probability random variable is equal to some value, right? Okay, so let me do an example of calculating a probability from a marginal distribution, right? Using this PMF over here, right? So as I said before, for the time being, let's pretend that we don't know that this came from a sample space on an experiment and so on, right? So somebody just gave me this PMF over here, right? What I want is I want the probability that the big X is equal to 1, right? So notice this is not joint over here. This is just a normal probability, right? Okay, so to get probability x is equal to 1, right, what you're doing is you're really just adding up the different cases, right? So you can have x is equal to 1 when y is equal to 0. You can have x is equal to 1 when y is equal to 1, x is equal to 1 when y is equal to 2, and then when y is equal to 3, right? And those are your 4 possible cases, right? So if you want a probability x is equal to 1, right, and these cases corresponding to events that are disjoint, right, to get probability x is equal to 1, you add for the different cases, right? Case when y is equal to 0, case when y is equal to 1, when y is equal to 2, and when y is equal to 3, right? So you add up all of those, right? Now, if you add in this over here, right, here I have it written out, right? But to write it in a more concise way, what you do is you can use summation notation, right? So you're indexing over this value small y, and remember the small y would be the values of the random variable, and those possible values would be 0 to 3, right? So this sum over here, this rather long sum, I can write more short in a shorter manner using this summation notation, where I'm taking this sum probability x is equal to 1 where y is equal to y, where this small y over here takes values 0 to 3, right? And when I write it out, I just get this expression here, right? Okay, so in the notes, right, your joint PMF, I can write this way as probability x is equal to x, y is equal to y, or I can write it as a function f of x, y, right? So so this over here, probability big X is equal to 1, Y is equal to Y, I can just write it as small f is equal to 1 minus y. This isn't hugely important over here. It's really just a little bit of notation. Why I'm doing this over here is that it's to really tie in with the definition for your marginal distribution of x that's given here, right? Okay, so probability x is equal to 1 would be sum of these probabilities here for different cases of y. We could put it in summation notation over here, right? And we just call in you just call in this joint probability over here as f of x, y, right? So probability x is equal to a certain value is really just going to be the sum of probabilities from your probability mass function when x is this particular value that you're working with, right? And then what you want to do is you want to sum over the possible cases of y, right? So that is what this definition is doing for you, right? Okay, so let's actually just work it out. So probability x is equal to 1, we sum in over possible values of y, and that would be y, small y takes values 0 to 3, right? And you add up the probabilities of those cases, right? Probability x is equal to 1, y is equal to 0, right? From your table, it's equal to 0. Probability x is equal to 1, y is equal to 1 from your table is 1/8, right? This one over here is a quarter, and this one is 1/8, right? So to get probability x is equal to 1, you just add up these probabilities, right? Which would be from your second row over here. Add them up and you get a half, right? Okay, and you probably realize that if you have a table like this, is a very fast way to do this, right? If you want probability x is equal to 1, right? What you're doing is, for this one over here, you're just adding up the probabilities in the row corresponding to the x is equal to 1. In other words, adding up the probabilities in your second row, right? Which is what I'm doing over here. And that will give you probability x is equal to 1, right? To get probability x is equal to 0, it's the same thing, right? All you're going to do is you're just going to add the probabilities on the first row, the row that's corresponding to x is equal to 0, right? Okay. Right, here I have this extra line over here that I don't really need. This is going back to the experiment, right? And the point I want to make over here is that the case when x is equal to 1, y is equal to 0, right? So I'm going back to the fact that this PMF over here came from a sample space, right? This is corresponding to the event with no entries, right? X is equal to 1, y is equal to 1 is corresponding to this event, right? Okay, so probability x is equal to 1, right, is when you have x is equal to 1, right? X is equal to 1, you want to remember, would be these four outcomes over here, right? And when you have x is equal to 1 and you split it up into different cases, y is equal to 0, y is equal to 1, y is equal to 2, and y is equal to 3, right? What you're doing is you're partitioning this event over here, right, into subcases corresponding to when y is equal to 0 and then when y is equal to 1. So for example, x is equal to 1, y is equal to 1 is this case over here, right? probability x is equal to 1, y is equal to 2 would be these two cases over here. And probability x is equal to 1, y is equal to 3 would be this last case over here with all heads, right? And there's no outcomes where probability x is equal to 1 and y is equal to 0. We talked about that, right? Okay, so when you're doing probability x is equal to 1 and you're splitting up your probabilities like this, right? In a sense, what you're doing is you partition in your sample space into disjoint events and you add in our probabilities. Okay, right, so that's marginal probability, right? Marginal probability, marginal distribution, probability in a marginal distribution in the case of x, right? And in the case of y, it's similar, right? What you're doing is you're going to be adding probabilities now, but what you're going to do over here, notice over here, what we're doing is we're arranging the y, right? So if we want probability x is equal to 1, you need to add up the cases for the different values of y, right? Okay, so that's why you're summing over the y over here, right? In the case of now over here, when you fix in the y, right, what you're going to do is you're going to change. Now what you want to do is you're going to change the values of x and consider the possible cases. And that's where this formula comes from, right? And the argument over here, the explanation is similar to what happened in probability for marginal distribution of x, right? If you want to work out probabilities in for a marginal distribution of y, right? If you want how you do it. Okay, so remember for, in the case of x over here, if I wanted probability x is equal to 1, what I did is I added probabilities along the row here, right? In the case of if I want to calculate for a marginal distribution for y, right? If I want probability that the y is equal to 2, right? Then what I'm doing is I'm using this formula over here. In the case when the small y is equal to 2, right? Okay, and what that means is, right, so this should be an x. Yeah? Okay, so using this formula here, where you running over possible values of x over here, right? Okay, right. So in this case, if I want probability y is equal to 2, right? What I'm doing is I want probability y is equal to 2 in the different cases when the x is equal to 0 and when the x is equal to 1, right? And this is when the x is equal to 0 and when the x is equal to 1, right? Okay, so probability y is equal to 2. What I'll do is I'll add this 1/8 to a quarter to get my answer, which is 3/8, right? And notice what I'm doing over here is now I'm adding along the column, right? Okay, so depending on how you have this, if you put x on the rows over here and y on the columns over here, if you want to get for marginal distribution of y, if you want to get a certain probability, what you're going to do is you really add up the probabilities in a column, right? So for example, as I just did, right, for probability y is equal to 2, you're going to have 1/8 plus a quarter, which is going to be 3/8, right? And similarly, if I want, say, probability y is equal to 0, what I'm going to do is I'm going to add 1/8 to 0 to get 1/8. Recall that the probability x equal to x, right? You can get from your joint PMF, right, as a marginal distribution, right? Okay, so on this probability x is equal to x, right? Given a joint PMF, this is a marginal distribution over here, and likewise probability y is equal to y, right? This is a marginal distribution over here, right? Now you could denote your marginal distribution for the big X is g of x, and the marginal distribution for the big Y is h of y, right? So this statement over here you can read as the joint PMF. In order for discrete random variables x and y to be independent, right? Your joint PMF of x and y has to be equal to the product of the marginal PMFs for x and y, right? Alright, so going back to our example where we toss a fair coin twice, right? We had random variable x is the number of heads on the first toss, and random variable y is the total number of heads, right? When in order to work out probability x is equal to 1, y is equal to 2, right? What we do is we consider the cases when x is equal to 1, which would be these four cases over here. And then the cases when y is equal to 2, which is these three cases here, right? Okay, so probability x is equal to 1, y is equal to 2 is when x is equal to 1, right? Now, when probability x is equal to 1, y is equal to 2 is when probability when x is equal to 1 and y is equal to 2, right? Now, x is equal to 1, as I said, is these four cases over here. And that's in fact a pre-image of 1 over here, right? So I can write that as pre-image of 1, right? And likewise, y is equal to 2, those cases over here, these three cases here, for y is equal to 2. You can write that as pre-image of 2, right? And for both of these, to get probability x is equal to 1 and y is equal to 2, what you're doing is you're actually intersecting the event when x is equal to 1 and when y is equal to 2 over here, right? Okay, so why I mentioned that? Is this working out this joint probability in the discrete case is calculating a probability of intersection of events over here, right? So this is when you have specific values, but more generally, what you have is this formula over here, right? So probability x is equal to x, probability y is equal to y. This x inverse x over here is when, for cases when the random variable x takes value small x, and this y inverse y is cases when your random variable big Y takes value small y over here, right? So these are pre-images here, right? And we just saw an example of this, right? Okay, so why I mentioned this is that here notice probability, your joint probability over here, I can write as the intersection of events. I remember that in order for you to have independence, right? Independence means that probability of an intersection of events is equal to the product of the probabilities of the events, right? Which is this here, right? Right, okay, so which is this over here, right? Probability A intersect B is equal to probability A times probability B, right? Alright, so the point I want to make over here is this definition, right? Where it's coming from is that probability x is equal to x, y is equal to y. You can write this as the probability of the intersection of events, right? If you have independence, then this is a product of these probabilities. Now, probability x inverse of this event, x inverse of x, means this. What this means is you're looking at all the cases where the random variable takes value x, small x, right? And that in fact is exactly the same as probability x is equal to x, right? And similarly, this probability y inverse y, right, is equal to probability y equal to y, right? Okay, so really, this definition over here is basically coming from your definition, this definition of probability for the intersection of events, because in a discrete case, calculating a joint probability over here is in fact calculating the probability of the intersection of events. Alright, so we have this problem here, right, which we looked at already, right? So we had a fair coin that we tossed 3 times, right? X is the number of heads on the first toss, right? And Y is the total number of heads, right? And the joint PMF, we worked it out actually be equal to this, right? And now what we want to do in this problem is we want to get the marginal PMFs, right? And we want to determine if random variables x and y are independent, right? Okay, so notice here, right, in order to check to see if random variables x and y are independent, right, what you're doing is you're comparing the joint PMF over here to the marginals, right? So if your joint PMF is equal to the product of the marginal distributions, then you have independence, right? Otherwise, it's not independent, right? Okay, so you need part 1 over here in order to do part 2, right? Because part 2 over here, you need marginal PMFs, right? Okay, so let's work this out, right? Well, what is your marginal PMF, right? Your marginal PMF is, well, what you want is probability x is equal to x for your different cases, right? When the small x, when the x is equal to 0 and when the x is equal to 1, right? Now, if I want probability x is equal to 0, as I said, what you could do is we could just add the probabilities in your first row, and when you add the probabilities in the first row, you're going to get a half. And to get probability the big X is equal to 1, right? Right, what you do is from your joint PMF, you add the probabilities on your second row, right? The row corresponding to X is equal to 1. And in this case, you'd also get a half, right? So your marginal PMF for the X, right, is probability that the big X is equal to 0, right? And you get that by adding your first row over here, and you get a half. And also probability big X is equal to 1, right? And you add that and get you add your second row to get a half as well, right? Okay, so this is your marginal PMF for random variable X, right? And similarly, if we want to get marginal PMF for random variable Y, right? What you'd need is the probability that the Y is equal to 0, Y is equal to 1, Y is equal to 2, and Y is equal to 3, right? And to get probability y is equal to 0, you add in these two joint probabilities over here in this column, right? So you'll get 1/8. To get probability y is equal to 1, you add these two joint probabilities here and you get 3/8. Right? X probability y is equal to 2, you're going to add 1/8 to a quarter, you're going to get 3/8. And then probability y is equal to 3, you add the 0 to 1/8, you get 1/8 over here, right? Okay, so this is your marginal PMF for y, right? Notice over here, this PMF, marginal PMF, is a PMF in the normal sense of the word for a single random variable here, right? Right. So now what we want to do is we want to determine if the random variables x and y are independent, right? Okay, so recall this, you're given a joint PMF over here, and for the big random variable x, you got its probability, your PMF, as a marginal distribution, and likewise the y over here, you got its PMF from a marginal distribution, right? Okay, so this is the PMF for x, and this is the PMF for y over here, right? And now what we want to do is we want to check and see if x and y are independent, right? Right, so how you check to see if x and y are independent, right, is you use this criteria over here, right? Or we could use this one. This is probably easier over here, right, to look at. Okay, so we want to check to see it's going to be independent if your for each x, y, each pair of value of the x and the y over here, this statement is whole, right? This statement holds, right? So what that means is that for each 8 of these positions over here, this statement has to hold, right? That your margin, the probability, your joint probability over here, right, has to be equal to product of marginals, right? Okay, right. Okay, so we can check that, right? Now, one way, if you have this over here, given this PMF here, right? You could in fact look at your PMF here, right? Given the sort of like small case, right? Where you only have a small amount of possible values for the x and the y, right? And so you have this small table with 8 entries. You can in fact get an idea of whether your random variables x and y are independent, right? Now, how you get an idea about it is you can look at the PMF over here, right? And in order for it to be independent, right, the rows have to be multiples of each other, right? So if you want to notice over here, right, this, if you take your first row over here and you multiply it by 1/3, right, you're going to get your third row over here, right? So your first row over here is a multiple of your second row, right? Okay, and likewise, if you take your first row over here, right, and you multiply it by 2/3, you will get your second row over here, right? So the rows are, um, well, if you look at it as vectors, the rows are dependent, right? The rows are multiples of each other, right? Okay, so if if your PMF is correspondent to when x and y are independent, right? The PMF, the rows, the probabilities in the rows would need to be multiples of each other, and not just the rows, the columns as well too, right? Because if, for example, you look at your first column over here and you look at your second column, you can get your second column from your first column by multiplying your first column throughout by 2, right? Okay, right. So this here is one way to identify if your joint PMF, if the random variables in your joint PMF are independent or not, right? You could look at the PMF, and if each of the row, all rows are multiple of a single row, and all columns are multiples of a single column, then you have independence, right? Now over here, first row over here is definitely not a multiple of a second row, right? Because if your first row is a multiple of the second row, then this entry would have to be 0, right? Okay, so here we suspect it's your random variables x and y are not going to be independent, right? But suspicion is not good enough, right? What we want to do is we want to show that random variables x and y are not independent, right? Okay, so in order to have independence, this statement must hold for each x and each y over here, right? It needs to hold for all of them, each x and each y, right? So if I can show that this statement doesn't hold for at least one, in other words, I find a counterexample, right? Then the overall statement will break down, right? The overall statement will be false, right? So to show that random variables x and y over here are not independent, we just need to find a counterexample. In other words, we need to find a value for x and a value for y such that your left hand side over here is not going to be equal to the right hand side, right? Okay, and probably if you're looking for a certain value to use, it's probably not a bad idea to try the 0, right? Although it most likely whatever pair of values that you choose, right, you'd see that this would break down, right? But let's go with this this 0 over here, right? So this 0 is when x is equal to 1, right? Sorry, this 0, yes, this 0 is when x is equal to 1 and when y is equal to 0, right? Okay, so we're looking at that case, right? So we're looking at when the x is equal to 1 and when y is equal to 0, right? And what we're going to do is we first figure out the left hand side over here, and the left hand side is coming from your joint PMF. So when x is equal to 1 and y is equal to 0, when x is equal to 1 and y is equal to 0, you have 0 on this side, right? Okay, now when x is equal to 1, right, what you want is this g of x evaluated at 1, right? Now remember what this g of x is, right? This g of x is just a marginal distribution of random variable x here, right? Okay, which is, this is your g of x over here, right? The g of x is the marginal PMF, the big X here, right? Okay, so what I need over here is g1, right? I'm testing this equality here. So I have 1, 0 over here. I need g1 and I need h0, right? And the g1 I can get from my marginal PMF that I worked out before, right? The g1 is a half, right? Okay, and I also need hy, right? And hy is the marginal PMF for the big Y, right? And I need hy, right? But what specifically I need is I'm looking at the case when x is equal to 1 and y is equal to 0, right? So what I need is y equal to 0 over here. So I need h0, right? And h0 from my marginal PMF, the h0 is equal to 1/8, right? Okay, so I check this now, right? On this side here, when x is equal to 1 and y is equal to 0, this joint PMF is equal to 0, right? This 0 here, right? This G1 over here is equal to half, right? And the H0 here is equal to 1/8, right? Okay, so I have 0 on this left hand side, and on the right hand side I have G1 times H0, which is 1 on 16, right? And which is not equal to 0. So what that says is that I found a pair of values x and y such that this statement doesn't hold, right? And this statement is just the same as the statement here that joint PMF is not equal to the product of the marginals, right? So x is equal to 1 and y is equal to 0, this statement doesn't hold, right? And because I found one counterexample, the entire thing doesn't work, right? So what that means is that the x and the y are not independent random variables. Right, so before I look at joint probability density function, right? In other words, joint when I have continuous random variables, let me just do a quick review of the difference between discrete and continuous random variables, right? Okay, so if I have a discrete random variable such as this one over here, right? A discrete random variable can be described by a PMF, right? So over here, these are possible values of your discrete random variable for this particular PMF probability mass function, right? Okay, so possible values for the big X would be 0, 1, 2, and 3, right? And probability X is equal to 0 is 1/8, probability X is equal to 1 is 3/8, and so on, right? Okay, so here I have this diagram over here, right? This is from MIT open lecture here, right? Okay, so this over here, this diagram is indicating a PMF, right? I'm not saying it's the same PMF as this one here, right? But this is a PMF. And the point is, for discrete values of X, you have a probability associated to it, right? Notice if you outside of you one of these discrete values, so for example over here, right? Here I have probability x is equal to 0 is 1/8 and probability x is equal to 1 is 3/8, right? If I have x is equal to half, right? Probability x is equal to half is actually equal to 0, right? So the probabilities are concentrated, if you want, at these discrete values here, right? For a PMF, right? When you have a discrete random variable, right? Now, on the other hand, if you have a continuous random variable, right, which is what this diagram over here is supposed to illustrate, is the possible values for a random variable now lie in a range such as this over here, right? So in this case, you're showing positive values of x, but it doesn't need to just be positive values of x. So while in the case of a PMF, right, you're only going to have uh, the range of values for the x would be either finite or probably countably infinite. In the case of a continuous random variable, the values that the random variable would take would lie on an interval, right? And in this, for this particular continuous random variable, it seems as if the possible values would be, well, the entire real axis here, right? Okay, now if I want to get probability for a probability mass function, right? And say if I want the probability for a discrete random variable with a probability mass function, I want to get the probabilities between A and B, right? What you do is, as they have over here, you mark the A, you mark the B, and then you add up the probabilities for all the discrete cases that lie between A and B, right? Okay, so in the case of a discrete random variable, what you're doing is you add in probabilities over here, right? In the case of a continuous random variable, if you want probability of your random variable lying in a range between A and B, right? Now you're doing something similar to the summation, but you're doing it in a continuous sense. And in a continuous sense means that you're actually going to integrate, right? Okay, so to get probability of a continuous random variable lying between a and b, what you need to do is you need to do an integral of your probability density function between limits a and b over here, right? Okay, now next thing too is you can compare certain properties of your probability mass function to your probability density function. Over here, this is saying that the probabilities are in fact must all be bigger than 0, and over here this is saying that your probability density function has to lie above your x-axis, right? Well, bigger than equal to 0, so it could touch your x-axis, but it can't go below your x-axis, right? So notice this property is corresponding to this property over here, right? This one over here is saying that the probability, sum of probabilities for a discrete random variable is 1, which is, as this case over here, if you add up these probabilities will add to 1, right? Now what this one is saying for in the case of a continuous random variable is if you add up all the probabilities, right? In other words, if you consider the probabilities from minus infinity to infinity, right? So if you add up the probabilities for all the cases, right? And in order to do that, you integrate from minus infinity to infinity. The sum of the probabilities that you're going to get in that way is equal to 1, right? Okay, so the point that I want you to get out of this is that the PMF over here for a discrete random variable and the probability density function for a continuous random variable, they have analogous properties, right? And one main thing to note is that for a continuous random variable, in order to do the summation, you need to do integration, right? Alright, so what we just saw is that if I have a single discrete random variable, this diagram over here is indicating a probability mass function, right? So at different values of x, you have a probability associated to it, right? And this diagram here, right, this is for a continuous case, right? Okay, so for a continuous random variable, the values of your random variable lie on an interval such as this. And if we want to get probabilities for a continuous random variable, we calculate probabilities not at a single point but on an interval, right? And to calculate probability of your random variable lying taking values between a and b, right? What you're going to do is you're going to integrate your probability density function, right? Between the limits a and b, right? So you use this formula here, right? Okay, so this is when you have a single random variable, right? So this is single discrete random variable, and this is single continuous random variable, right? Now, what we're talking about right now would be joint random variables, right? So I spent some time talking about joint discrete random variables and how you describe the probability for joint for two random variables, right, is using your joint PMF here, right? Now the thing about a joint PMF is that you have two random variables x and y, right? The x can take certain values and the y can take certain values, right? And in fact you can plot this, right? Similar, so this is discrete when you have one random variable, and this is discrete when it's a joint case, right? In other words, you have two random variables here, right? And plotting this, you can plot this using a line diagram similar to this over here, right? And the plot of it would look like this here, right? So the plot of this PMF, joint PMF is, and this is in the course notes, right, is this over here, right? So notice, for example, at right, most of these probabilities over here, well, 0 except the ones on the diagonal. This particular PMF, I was using it illustrate a point, right? But let's just see that when x is equal to 1 and y is equal to 2, right, you have a probability of a half, right? And that's what's showing up over here, right? This axis, this is the x-axis over here, this is your y-axis, so this is a three-dimensional picture, right? And similar to what you would have seen in your MATH2240, right? So your xy plane is on your bottom over here, and this over here, this is your z-axis, right? Okay, so at x is equal to 1 and y is equal to 2, you have a probability of a half, right? And you can plot that probability using a single line over here, usually with a dot on top here, right? And the height of this green line over here is a half to indicate that you have a probability of a half at x is equal to 1 and y is equal to 2, right? And similarly, say at x is equal to 0 and y is equal to 0, you have a probability of a quarter, right? Which is what you see in from your PMF, your joint PMF table over here, right? Okay, so the point I want to make is this is a line diagram, example of a line diagram in when you have a single discrete random variable, and if you have two discrete random variables over here with a joint PMF, this is what your line diagram is going to look like, right? So your line diagram is now going to be you're going to plot it in three-dimensional space. Okay. Okay, and what your joint PDF is going to look like, right? So your joint PDF is going to be a function of x and y, right? So down here you have your xy plane, right? So this is similar to what happened in the discrete case, at least down here, right, in plane, right? So your random variable can take different values of x, right, and different values of y, right? So random variable x would take different values of x, random variable y would take different values of y. And what you're doing is you're looking at pairs down here in the xy plane, right? And in this case, the joint probability density function is you're going to have the graph of it is going to be a surface in three-dimensional space, right? Okay, so in the case of a single continuous random variable, your PDF, which is this f of x over here, right, is a graph, right? And this graph in single random variable case is going to be a curve in the xy plane, right? In the case of when you have two random variables now, the x and y, right, your PDF, your joint PDF is now going to be a surface in three-dimensional space. Okay, so your joint probability density function for two continuous random variables x and y we just saw is going to form a surface view in three-dimensional space, right? Now this joint PDF over here has similar properties to your PDF in single continuous random variable case, right? So single continuous random variable case, your PDF over here, notice it lies above your x-axis, so your PDF here, right? It's bigger than or equal to 0, right? So likewise over here for your joint PDF, right? Your joint PDF, the function of x and y now is going to be bigger than or equal to 0. In other words, the graph that you have, right? Right, so this graph over here, the graph of your joint PDF, right, it's going to lie above your xy plane, right? Okay, and next property that you have single continuous random variable is that when you integrate this the PDF a single continuous random variable. In other words, when you integrate f of x, right, and you integrate for all possible values, right, in other words, you integrate from minus infinity to infinity, right, you get a value of 1, right? Likewise over here, right, for your joint PDF, if you integrate it over the entire xy plane, right, so this is your joint PDF, and if you integrate over the entire xy plane, in other words, for all possible values of x and y, right? Well, what you're doing is you sum in probabilities, and when you sum probabilities for all cases, the probability has to work out to 1, right? So that is where this 1 is coming from over here, right? Okay, so this is properties of a joint PDF, right? The graph, the function of the two variables here, this joint PDF, needs to be bigger than or equal to 0. And when you integrate over the entire xy plane, you're supposed to get a probability of 1 over here, right? Okay, now notice here what you do is if you want to get probability in a range, right, of in the case of a single random variable, if you want to get probability that the x lies between a and b, right? What you're doing is you integrate your PDF, right? Between values a and b, right? And when you work out this area over here, right? When you work out your definite integral, this area here is going to be equal to a probability, right? Now, it's a similar sort of thing when you have a joint PDF, right? So this is a general case over here, right? Before we get to this general case, let me just do specific case when your region R over here, this is a rectangular region, right? Okay, so if I want to get the probability, right, that my random variable is taking values in a region R, where that region R is a rectangular region. So you're going back to the rectangular regions that we saw when we did double integrals. Right. Okay, so if I want to get the probability that my random variable is taking values inside a rectangular region like this over here, right? How you're going to do it is, well, you're going to evaluate a double integral, right? And you're going to evaluate a double integral for limits, right? And the limits, where these limits are coming from, the limits are coming from what's specified by this rectangular region over here, right? So in this case, the rectangular region is that the x is lying between a and b, right? And y is lying between c and d, right? Okay, so integrating, anyway, so if I want to get the probability that my random variables x and y are lying in this region R, right? The values of my random variable are lying in this rectangular region R. What you're doing is you're doing a double integral of your joint PDF over this rectangular region, right? And you're using the methods that you know from MATH2240, right? For your rectangular region, you need to determine the appropriate x limits and y limits. And those are going to form these y limits over here and these x limits over here, right? Okay, now this is for your random variables x and y taking values in a rectangular region, right? And more generally, this region over here, which we again saw in MATH2240, right, is you can integrate over regions R over here that are not necessarily rectangular, right? You could integrate over type 1 regions, type 2 regions, and so on, right? Polar rectangles, etc., right? We're not going to do that for MATH2240, right? In this case, if we want to get probability of random variables lying in a region, right? Your region that we're going to work with would be rectangular regions in this class, right? Okay, in which case you're using this sort of setup over here, right? Matter of fact, you could always just, well, almost always just integrate with respect to y, then with respect to x. Have your y limits over here and have your x limits over here, right? But more generally, if your region R over here is not necessarily rectangular, right? Well, then this is how you describe it, right? What this means is if I want to get probability that my random variables x and y take values inside a region R like this, what you do is you work out a double integral over this region R over here, right? Get the probability that the big X is equal to certain small x over here, right? What you're doing is you sum in probabilities from a probability mass function, right, over all possible values of y, right? So, and this, what we do in here is we fix in the small x for the time being and sum in over the y, right? So, for example, fix in the small x is equal to 0 over here. And what we do is if we want to get probability or that the big X is equal to 0, right, we're going to sum from your probability mass function, right, when the small x over here is equal to 0 and you sum over all possible values of y, right? So in other words, you sum in the 1/8 plus the quarter plus the 1/8 plus the 0, right? And that will give you probability x is equal to 0, right? Okay, so we saw that already, right? So getting your marginal distribution, right, for any possible value of your random variable x, what you're doing is you sum in your PMF, right, over all possible values of y, right? And likewise, to get your marginal distribution of y, right? So for a given y over here, to get probability y is equal to y, what you're going to do now is you're going to, for example, if you want probability y is equal to 1, right? You're going to sum over all possible values of x, right? In other words, you're summing along the column, right? Okay, so here, to get your marginal for x, right, you sum in your probability, joint probability mass function over possible values of y, and um, to get marginal distribution of y, right, you sum in your probability mass function over possible values of x, right? Okay, so this is marginals in the case of joint discrete, right? And now what we want to look at is marginals in the case of joint continuous, right? Okay, so in joint continuous, what I have is analogous to my joint PMF. Now I have a joint PDF, right? Probability density function, right? What I want is I want for a random variable x over here. Okay, so in this case, right, in the discrete case, what you get out of this by summing over y, right, is in fact you get a probability mass function for the random variable x over here, right? Okay, so in this case now, what you have is you have a joint density function for the random variables x and y, right? And what we want is we want a probability density function for the x, right? Okay, and to get the probability density function for the x, right? You're doing the same sort of thing, right? Here, what you're doing in the discrete case is you are summing over uh, all possible values of y, right? Now, likewise over here, right? From your joint PDF to get the PDF, the normal sort of PDF, single random variable x, what you do is you sum your joint PDF over all possible values of y, right? And in the continuous case, how you do your summation over here is via integration. Okay. Right, and likewise, what we want is we want a marginal PDF, marginal distribution for random variable y, right? And how you get that is you do in the discrete case, you do the summation over x, right? Over possible values of x. And in this case over here for your joint PDF, right? What you do is in this continuous case, if we want a marginal, if you want the marginal PDF for y, right? What you're doing is you sum in over all possible values of x, right? But in this case, the summation is an integration, right? So you integrate your joint PDF with respect to x between x values minus infinity to infinity. Alright, so we saw in the discrete case, if we want to check to see that random variables x and y are independent, right? What you could do is you can use this check for this criteria over here, right? So your left hand side over here, this is your joint PMF here, right? This g of x is marginal PMF for x, right? This h of y is marginal PMF for y, right? And if you have independence, then you'd have an equality over here, right? That the joint PMF is equal to the product of marginal PMF for x and marginal PMF for y, right? Now, similarly, if we want to check to see if continuous random variables are independent, right? You really basically doing the same thing, right? Except in this case over here, right? What you're working with is probability density functions, not probability mass functions, right? Okay, but other than that, it's the same formula, right? So this here is, if you want to check for independence, what you do is on the left hand side over here, you have your joint density function, right? And then on the right hand side here, this g of x here is your marginal PDF for x, right? And the h of y is the marginal PDF for y. Okay, and x and y are independent if your joint PDF is equal to the product of the marginal of x times the marginal of y. Alright, so we're going to take a look at this problem here, right? We have two continuous random variables, and you're given a joint PDF. Well, you're given basically everything about the joint PDF except you're not told what this constant c is over here, right? Okay, so the first thing in question is you want to determine the value of c, right? Now, how you're going to determine the value of c, right, is you're going to use the fact that when you sum probabilities is going to be equal to 1, right? And in a joint probability density function, summing the probabilities would be integrating over the entire plane, right? Okay, so you need to do this double integral from infinity to minus infinity, right? For limits x and y, right? When we work out the integral of this function of x and y, right, when we integrate over the entire plane, right, what we're going to end up getting is you're going to end up getting an expression in c, right? Well, okay, so this would be how you do it. You have your f of xy given to you over here, right? You're going to integrate over the entire plane, right? Now, this integral over here is supposed to be equal to 1, right? And this is what's specified in the question, right? When you do this double integral over here, what you end up with is you end up with an expression in c, right? So working out your double integral on your left hand side over here gives me this minus 125c, and on the right hand side over here I always have 1, right? So I end up with an equation involving the c, so I'm able to figure out what the c is, right? So let's work out part A, right? As I said, what you need to do is you need to use this property of a joint probability density function, right? Okay, so this is the f of xy specified for you, right? Notice how it's specified that this joint PDF, right, is equal to this function within this rectangle where the x lies between minus 2 and 3. The y lies between 4 and 6, and it's 0 everywhere else, right? So let's see what that actually looks like, right? Okay, so this is a function in two variables. When you graph it, you're going to get a surface in three-dimensional space, right? Now, this function over here is non-zero only for the values x lying between minus 2 and 3 and the y lying between 4 and 6, right? So this is what the graph is going to look like. Your function is 0 everywhere else except on this rectangle, right? So let's project down so you can see the rectangle. Okay, so that's my function of xy. As I said, it's 0 everywhere except on your rectangle, right? So projecting down gives me right. So this function, right? Your function is non-zero between minus 2 over here and 3, right? And between y is equal to 4 and y is equal to 6 over here, right? Everywhere else the function is equal to 0, right? So the function is only non-zero for values of x between minus 2 and 3 and y lying between 4 and 6, right? Okay, so if we're going to integrate this, right, integrating your function is 0, right, everywhere except on this rectangle specified over here, right? Okay, so if we're going to be integrating, right, all we need to do is we just need to integrate over this rectangle, right? and the rectangle is right this rectangle in the xy plane, right? Okay, so integrating this function over here, right, over rectangle. I'm integrating with respect to y first, then with respect to x. Your y limits you see in over here would be 4 and 6. Well, actually, it's just specified for you over here. Y limits lie between 4 and 6. And the x limits lie between -2 and 3, right? Which would be -2 and 3, right? Okay, and as I said, the function is 0 everywhere else except on this rectangle here, right? So all I need to integrate is, as I said, on rectangle for x values between -2 and 4, and the y values between 4 and 6, right? Okay, so that's what I'm doing over here, and this is your double integral over this rectangular region. You do this in a standard way, right? You integrate with respect to y first, right? So when you integrate the y over here, you're going to get y squared on 2, right? You put in your y values, y is equal to 6 and y is equal to 4, right? And when you put in the 6, you're going to get 36 on 2, which is 18. When you put in 4, you're going to get 16 on 2, which is 8, right? So far, this is what I have, right? And now I still need to integrate with respect to x, right? This over here is 10c x minus 3. And when I integrate the x minus 3, I'm going to get x minus 3 squared on 2, right? Okay, and you put in your x values now 3 and -2, and when you do that, right, the 3 over here will give you 0, right, and the -2 would give you right, -5 squared, which is 25, right, and then this 2 divided by 10 gives me an x5, which is 125, and remember I'm subtracting for this second limit over here, right, so I get -125 on c, right? Okay, so if you try to figure out what the value of c is, right, and for this sort of problem here, for this problem, right, what you're doing is using this probability, this condition for a joint PDF, right? This condition for the joint PDF means that if you integrate the joint PDF over the entire xy plane, it's supposed to get 1, right? And this is your joint PDF over here. It's defined for the entire xy plane, except it's only non-zero on this rectangle over here, right? So to do the integral, so this is just reviewing here. To do a double integral, all you need to do is integrate over this rectangle specified here, right? When you on this side over here, you're working out the double integral, and you're going to get an expression involving c, which is this -125c. And on the right hand side here, you always just have the 1, and this allows me to figure out that the c is equal to -125. Now I want to do this part over here, right? I want to get the probability that the random variable x takes values between 0 and 1, and the random variable y takes values between 4 and 5 over here, right? Now you want to remember what this means, right? What you want over here is you want the probability that the random variables x and y take values inside a region, right? And in this case, the region specified over here is a rectangular region, like such as this over here, right? Okay, so your random variable x and y, it's going to take values in this rectangular region over here, and you want the probability that random variable, the values lie in this rectangular region, right? And how you do it is you integrate your joint PDF, right, over a specified region, right? And in this case, the region R is rectangular, right? Okay, and if it's a rectangular region, you use the method for evaluating a double integral over a rectangular region, right? Okay, so you have your, just like what we just did, right? You'd have your y limits between c and d, and then you have x limits between a and b, right? So this really is the formula that we're going to use to work out part b, right? Okay, so what is part b again, right? So I want to work out probability that random variable x lies between 0 and 1 and random variable y lies between 4 and 5, right? In other words, the x and y lie in a rectangular region, right? And really, I can just use this over here, right? So what you're doing is you're integrating your joint PDF, right? Over a rectangular region, and you're doing it in a standard way, right? Okay, and I'm using exactly this formula here, right? So in this case, this minus the joint PDF that was given to you was this over here, right? And what you did in part A was figure out what the C is, right? So the C is minus 1 on 25, right? Okay, so this over here, inside here, this is your joint PDF, right? And you're integrating over a rectangular region, right? So integrating over a rectangular region like this, yeah? Okay. Right, so this diagram over here actually is showing me, showing what the joint PDF is, right? So the joint PDF is this orange part over here, and the region R that you're integrating over is this region R, this blue region R in the XY plane, right? Okay, so you integrating f of xy over this rectangular region. Right now, it may not seem as if that rectangular region lies below your graph, right? But actually it does, right? If you project down, you'll see that it, right? You see that it, in fact, it lies, right? The rectangular region lies below your graph over here, right? Okay, so this is what we're integrating over, right? We're integrating over this rectangular region. Matter of fact, it's a square region that we're integrating over. Okay, and to work this out, you work it out in your standard way, right? This is my function over here of two variables. I'm integrating with respect to y. Then with respect to x, the working over here is very similar to what we had from part A, right? Here, when I integrate this, matter of fact, this is this particular double integral, we get in fact, because what you have is a function of x over here times a function of y, right? This, in fact, you could work out in a somewhat fast way, right? So if I have a function of x times a function of y, right, and I have a double integral here, right, what I can do is integrate x separately, integrate the y separately, and then just multiply it, right? And that's actually what I do over here, right? Okay, so integrating the x over here would give me, and I pull the minus 1 on 25 out before I start integrating. So integrating the x minus 3 over here gives me x minus 3 squared on 2. Integrating the y with respect to y gives me y squared on 2 over here, right? I evaluate the integral with respect to x over here for using the x limits, which would be 1 and 0, and integrate, evaluate this expression with the y using the y limits, which would be the 5 and 4, right? Okay, and I substitute it in over here, and I get my answer, which is 9 on 100. The next part of our question over here is you want to work out the marginal PDFs, right? So the marginal PDF for random variable x, how you get it is you integrate your joint PDF with respect to y, right? Over all the y values, right? Okay. Right, so let's look at this over here and consider what happens for different values of x, right? Now, you want to remember that the joint PDF that we given in the question, right? It's only non-zero on the rectangle where rectangle of x being between minus 2 and 3 and y between 4 and 6 over here, right? So everywhere else, this joint PDF is equal to 0, right? Now this over here, this is my x-axis here, and this is my y-axis over here, right? Now what I want to do here is I want to calculate this marginal here, right? This g of x, right? Now, the marginal over here, right, it will depend on what the x is, right? Okay, so what you want to notice for this joint PDF, as I said, right, it's only non-zero in this rectangle. So if I'm working out g of x over here, right, so if I'm working out g of x over here, what I'm doing is I'm integrating at this point, say over here, let's just use this minus 3. Yes, this minus 3, right? So the the PDF is non-zero between minus x is equal to minus 2 and x is equal to 3 over here, right? So if we consider this point over here, x is equal to minus 3, right? Would we, at x is equal to minus 3 over here, you'd be integrating your PDF, right, over y values, right? So integrating over the y values over here, right? These are the y values. The y values are what's along your y-axis here, right? The green y-axis, right? But if you at x is equal to minus 3, right, this function over here is just 0, right? The only way your function is non-zero is between x is equal to minus 2 and 3, right? So at x is equal to minus 3, right? At x is equal to minus 3, over here your function is 0, right? So when you're integrating with respect to y, all you're doing is you're just integrating 0 with respect to y, right? So that's at minus 3, right? And that's also at minus 4, right? Matter of fact, at all values for x less than minus 2, right? When you're doing your integral with respect to y, right? All you're doing is you just integrating 0 because this function over here is 0 when the x is less than minus 2, right? So anywhere over here, right, for any value of x on that is less than minus 2, when you integrate in with respect to y, all you're doing is you're just integrating 0, right? So what I'm saying over here is when x is less than minus 2, this g of x over here, because you just be integrating 0. When x is less than minus 2, you're just integrating 0, right? So you will just get 0, right? Okay, and likewise, when the x is bigger than 3, right? If you consider n over here, and you consider and say x is equal to 4, right? When you integrate in with respect to y, right? All you're doing is, well, this function over here, when the x is bigger than 3, such as the 4 over here, your function is 0, right? So all you'll be doing is you just integrate in 0, right? And when you integrate 0, you get 0, right? So this g of x, the only place where you only get something that is meaningful and non-zero is between minus 2 and 3, because that's where your original joint PDF is non-zero, right? Okay, right, so let's work that out, right? So between, for the x line between minus 2 and 3, so the x line between minus 2 and 3, right? You want your marginal, so you want the g of x. Okay, and this is the joint PDF that we know from before. All we need to do is just integrate it with respect to y. Right? Now, this is an integral from infinity to minus infinity, right? And these are y values, right? So what that means is that you integrate in from minus infinity over here for the y to plus infinity, right? But again, this function here is non-zero only between y values 4 and 6 over here, right? So if you're doing your integral over here between minus infinity and infinity, all you're going to be doing is the only thing that's going to contribute to this integral over here would be the values between 4 and 6. So that's how I get this 4 and 6 over here. And now once I have this set up, all I'm going to do here is integrate with respect to y. I get y squared on 2, right? Then I put in my y values, and it works out to be this over here, right? Notice when I put in my y values here, right, I'm still left with the x here, right? I'm not putting in anything in for x, right? So the expression that I end up with over here is a function of x, right? So this here, this is the marginal density function for the random variable x here, right? Be a little more precise than that. What I should do is this here is the marginal PDF, but this is holding for x line between minus 2 and 3, right? In the other cases, when the x is less than 2, the marginal is equal to 0, right? So when x is less than 2, less than minus 2, it's equal to 0. when x is bigger than 3, the marginal is equal to 0. So this is how I should more precisely state it over here, right? The g of x is equal to this function minus 2x minus 3 on 25 between minus 2 and 3. And it's going to be 0 for x less than minus 2, and it's going to be 0 for x bigger than 3, right? So that's how you state it over here. It's non-zero between minus 2 and 3. It's equal to this function between minus 2 and 3. But everywhere else, namely when x is less than minus 2 and when x is bigger than 3, it's equal to 0, right? So you just say it's 0 otherwise. Right, and now what we want is we want the marginal distribution for y, right? And this is how the definition of how you get marginal distribution for y, right? You integrate the joint PDF with respect to x, right? Right, so again, this is using, of course, the same joint PDF over here, right? And if I project down, right, project, right, you see in that, right, we want marginal h of y over here, right? Now, for your different values of y, something similar is going to happen to what happened for x, right? So for example, over here at this y is equal to 3, right? What we need to do is we need to integrate this joint PDF, right, over all the values of x, right? Now, all the values of x, this is your this red axis over here is x-axis, right? So if at y is equal to 3, I want to get h of 3, right? What I'm going to be doing is I'm going to be integrating my joint PDF, right, at y is equal to 3 over all values of x here, right? But your joint PDF is actually equal to 0, right, at 3, right? The only place this joint PDF is non-zero, right, is between y is equal to 4 and y is equal to 6, right? Okay, so what that means is that for values of y less than 4, if I try to work out this marginal over here, all I'll be doing is integrating 0 here, and I will just get 0, right? Okay, and similarly, when the y is bigger than 6, right? When I attempt to work out my marginal, this joint PDF is going to be 0 over here, right? Okay, so if I'm integrating 0, right, along the x-axis in the x direction for all x values, I'm just going to get 0, right? So marginal of y is equal to 0, right? Less for all values less than y less than 4 and all values y bigger than 6, right? Okay, and on the interval between 4 and 6, right, the joint PDF is now non-zero, right? So we need to consider it, right? Okay, what you're doing here is you integrate in your joint PDF between, by definition, between minus infinity and infinity. So minus infinity x over here to plus infinity x over here, right? Now this function, right, your joint PDF, if you consider in the x direction, it's 0 before x is equal to minus 2, and it's 0 after x is equal to 3, right? So if you integrate in, right, all you'd need to do is, in order to work out your integral, all you'd need to do is integrate between minus 2 and 3 over here, right? Okay, because if you integrate anywhere else, all you would do is you just be integrating 0, right, which will just give you 0, right, which would not contribute to your answer, right? Okay, so all I need to do over here is integrate so integral for the dx between minus infinity and infinity, right, reduces the integral between minus 2 and 3, right, which is what I have over here. And now I just use my definition. I'm integrating with respect to x over here, right? When I integrate the x minus 3, I'm going to get x minus 3 squared on 2. And I put in my x values, x is equal to 3 and x is equal to minus 2. And this is what I get, right? Notice my answer over here involves y, right? It is y on 10. And again, I should be more precise about this. Your marginal between y is equal to 4 and y is equal to 6 over here is y on 10, right? And if we consider y less than 4, it's equal to 0. And if consider y bigger than 6, it's equal to 0, right? So your marginal here is equal to y on 10 between 4 and 6, right? And it's 0 otherwise, right? So it's what that means, it's 0 for y less than 4 and it's 0 for y bigger than 6. So now what we need to do is we need to check to see if x and y are independent, right? Now how you check to see if x and y are independent, right? How we're going to do it in this class is we use this criteria over here, right? So we want to check to see if my joint PDF is equal to the product of the marginals, right? And I just worked out what the marginals were, right? I worked out marginal g of x for x and marginal h of y for y, right? Okay, so let's check this condition, right, for this problem, right? Now, you want to remember that my function joint PDF, right, is non-zero, right, only between the on this rectangular region over here, right, x line between -2 and 3 and y line between 4 and 6, right? So how we gonna check this condition that the f of x y is equal to g of x times h of y, right, is we will check it on this rectangular region and then we will check it outside the rectangular region, right? Okay, so first of all, on your rectangular region over here, right, this is what the f of x y is, right? It is just minus 1 and 25 x minus 3 times y, right? So this is the joint PDF over here, right? And on this rectangular region, right, well, what's the g of x, right? The g of x we found, right, the g of x is equal to minus 2 x minus 3 on 25, and that's between my x line between -2 and 3, right? Okay, so remember what we're doing is we're just considering this rectangular region, right? And the g of x over here, right, if we consider in the rectangular region, it means that we're looking at when x lies between -2 and 3, right? Or when x lies between -2 and 3, this is the g of x over here, right? Minus 2 x minus 3 on 25, right? Okay, and similarly, if we consider in this rectangular region also, right? For this rectangular region, we have y line between 4 and 6, right? So the marginal for y, right, between 4 and 6 is y on 10, right? Okay, so minus 2 x minus 3 on 25 g, right? Minus 2 x minus 3 on 25 for the g, right? And then the h of y between under this rectangle over here is y on 10, right? Okay, and does this hold, right? Is f of xy equal to g of x times h of y, right? Yeah, it holds, right? Because what you'd have is when you multiply the g of x times the h of y, right? This 2 over here will cancel with the 10, right? So you get 125 on the bottom, which is the same as just 125. And everything else is the same, right? I have x minus 3 times y over here and x minus 3 times y over here, right? So on your rectangular region, I do have this equality. Okay, but what about outside the rectangular region? Let's say, for example, if you are, let's say I'm over here, right? Okay, so over here, right, this is when, if I'm over here, right, this is where the y is less than 4, right? Okay, so if I'm over here, right, where the y is less than 4, well, this f of xy, right, is non-zero only when the y is between 4 and 6, right? So if you're over here, right, the f of xy is going to be equal to 0, right? Okay, but if you're over here also, right, when the y is less than 4, right, the h of y is actually equal to 0 as well, right? So on this side over here, right, for the y less than 4, on the left hand side you have 0, and on the right hand side over here, right, the h of y for y less than 4 is actually equal to 0 as well, right? So you see if you're outside of R, right, at least in this case when the y is less than 4, the joint PDF is 0, and then this marginal h of y is equal to 0, right? And you can keep checking everywhere else, right? If you're outside of R, right? For example, now if you're over here, right, where the x is bigger than 3, right, what you're going to have is the f of xy is going to be equal to 0, right? Okay, and the marginal g of x is now going to be equal to 0, right? So the point is, if you're outside of R, right, the f of xy will be 0, and in this product over here, at least one of the marginals is going to be equal to 0. So you'd always have equality, right, where you're going to have 0 is equal to 0, right? So what that means is that the f of xy is equal to g of x times h of y, right, for all x and y, right? And for all x and y, how we did it is we just subdivided into the case um, where the joint PDF was non-zero to start off with, and then outside of that, right? Okay, so in other words, inside the rectangle over here and then outside the rectangle. And for all pairs x and y, we have that this equality holds, right? That f of xy is equal to g of x times h of y. Okay, and therefore that means that random variables x and y are independent.